I'm Dan Gauthier. I'm with Ohio State. I also have a startup company, ResCon, that I have to tell you about because there's a conflict of interest here. So this work is really led by graduate student Robert Kent and a former postdoc, Winsome Barbosa. So I'll be showing how to use this next generation reservoir computing, which we just heard about in the previous talk, to develop a nonlinear controller to control the dynamics of an experimental system. In this case, it's an electronic circuit that shows chaos. And the idea is that I'm going to have some kind of sensor that measures the dynamics of the circuit. I have some desired behavior that I want the circuit to do. And I'm going to use machine learning to allow me to control arbitrary states in the system. So I'll give just a brief introduction to now what's an old topic on controlling chaotic dynamics. Then I'll talk about how we can use machine learning to superpower these control techniques. Then I'll say a little bit about this next generation reservoir computing and how we use it for doing control. And I'll show you a few experimental results. So the general idea of feedback control is that I've got some kind of system. Sometimes this is called a plant in the control literature. This plant generates signals that hopefully you can poke and prod with attach some sensors to it so that you generate signals that you can then use for estimating the state of the system. You then compare that to the desired behavior that you would like the plant or the system to follow, and you design some kind of controller so that you drive the system to the state that you'd like it to go to. So this is a closed loop feedback type system. And the standard approach that has been known for decades, maybe centuries, it is a proportional integral differential controller, or PID controller. And the idea is that you've got some plant, you have something that you can measure with your sensors. You compare that measurement to the desired behavior, R of t, and then you form a control perturbation. E of t is just the error, the difference between where you want it to be and what it's currently doing. So you have some gain factor k that's just related to the error. So this is the proportional part of it. You can take a derivative of that error, multiply it by a gain factor for the differential gain, and then you can also integrate up that error over a long time. And you sum all these to try to control the plant. And the problem with these PID controllers is that the plant may have very nonlinear behavior that we're familiar with in chaotic dynamical systems. The good part is that this is very simple. There's very well-defined rules for how you tune up these gains. You kick and perturb the system, see how the plant responds to those kicks, U of t, and then that will allow you to, by analyzing those signals, to set these gains. So it works great. It's very simple. It's computationally fast. And this is what you'll usually see in embedded systems. So imagine something out in the field, you have no computer to hook it up to, or maybe you've just got some kind of embedded processor, what's now called an edge computing device. It can very easily calculate this behavior, but it really assumes linearity of the plant or the process you're trying to control. So now when we're faced with something that shows something as complicated as chaotic dynamics, this is the Lorentz attractor, and hopefully we're familiar with. The question is, how do we control something that is as complicated as this? The linear controller might only work at a tiny point in the phase space, but it's not going to work over the entire space. So it was Ed, and I see he's sitting here in the audience, back centuries ago, came up with a technique for controlling chaotic dynamics. And what they realized is that there are a skeleton of unstable periodic orbits embedded in the chaotic attractor, and that these give us a target for trying to do control. So the idea is that for that Lorentz attractor, there are an infinite number of unstable periodic orbits. I just show a few of them here, that if you were to put the system precisely on one of these orbits, and if there were no noise that would perturb the system, that it would stay there forever, and true for all these other ones. But there is noise. You never can put it exactly on the orbit. So even if it goes close to one of these orbits, it's eventually going to leave. And we think of that strange attractor with the butterfly as being draped on a skeleton of all these, that the system is going near one of these orbits and then it leaves, goes near another one. But that gives us a way for trying to do control. And so the idea that they came up with was to take the space and, let's say, create a surface of section and look for when a trajectory pierces that surface of section. And so the idea is that if this is one of the unstable periodic orbits, if I were to just look at one point of where it pierces that surface of section, what we can find either theoretically if we have the equations or experimentally by just watching the dynamics as it comes in the neighborhood of this point, is that there are stable and unstable directions. We have to have an unstable direction because we know it's an unstable periodic orbit. Trajectories have to eventually leave that point. But I can try to target this for control. And if the trajectory is in a neighborhood of this point, I can actually use linear control techniques in the neighborhood of that point. As long as I learn these unstable and stable directions, I can, let's say, kick it if it was going in an unstable direction onto a stable direction, and that will naturally go to the point. So linear control techniques can work well, but in a neighborhood of one of these unstable periodic orbits. And of course, it requires some kind of accessible system parameter. That is a knob that I can perturb. We need that for any type of feedback controller. Okay, so how can we bring machine learning into this? And I'll do this brief introduction to next generation reservoir computing. We're going to plug that into one of these feedback controllers. And the idea is that I'm going to use a specific type of feedback control that's known as feedback linearization. It is trying to learn the nonlinear dynamics of the system and essentially, through the control perturbation, cancel out that nonlinear behavior. So I turn the system into a linear problem, so then it's easy to do control. And this has been around for decades. It's usually hard to do, though, because you need a very good model for the underlying system. But instead of trying to create a physics-based model, we're going to bring in a machine learning model for trying to achieve this goal. So I'm also thinking that, maybe it's going to be on the next slide. What I should say is that in almost any experiment nowadays, we don't build analog circuits anymore for trying to do control. I used to do that a long time ago, but now any type of modern system is going to have an analog to digital converter that's going to take that underlying analog signal, turn it into a digital number, and then I'm going to have some kind of control algorithm. I then send that out through a digital to analog controller to then perturb the system. And so it's inherently a discrete system because I'm sampling at some interval. And so I really should be using concepts from discrete time control. And there's this old book. Let's see if I can hide this. Thank you. So there's this wonderful book that was published quite a while ago by Sargapani that essentially sets out how do you do this feedback linearization using any machine learning model that you want. It's a very good book. I stumbled on this quite a while ago, and it really cleared up how would we use reservoir computing for trying to do discrete time control. So now it will not advance. Okay. Great. Okay. So just a tiny bit of math of how this works. So we're assuming that the underlying nonlinear dynamics of the system is described by some kind of mapping. This would be a flow that takes us from the current state of the system into the future. This flow could depend on other past states too. So I'll call this F prime. Now, I don't necessarily have a sensor that can measure everything about the system. So my sensor might have just a projection of states that are there. So I'll say that Y is this projected or measured state of the system. And we're assuming that there is some mapping from the underlying states of the system. U's are my control perturbations, the knobs that I can turn for trying to change the state of the system. And then Y is just what I can actually get out of my sensors, what I can measure. Here, I've only got the control perturbations from states further in the past. UI is the perturbation that I apply now to try to perturb the system. So I've pulled this out, especially from this problem. And so the one limitation of the approach that we're using is that I can only have an additive control perturbation. There's many controllers that are of this form, but that is a limitation of this approach. Now, what Saragapani says is that to try to do this feedback linearization, you should take your control perturbation of this particular form, and I'll try to walk you through each one of these terms. So if I have a hat over here, that means it's a learned behavior. So I don't have access to F, I don't have access to W, how those control perturbations couple into the system. So I have to learn these through some kind of machine learning technique. And the idea is that let's try to insert this up into here. So if I have learned this, it should be counteracting the WU there. So they're just canceling. And then you see there's a subtraction of F showing up here. So I'm essentially subtracting the entire flow by this type of perturbation. And then E is the error between the actual state of the system and the desired state. So just like in my diagram for the system, this is just the error signal. Ed?
Is that term WU, is that a linear term or is that non-linear?
It's a linear term in general. Yeah, so let's say linear, nonlinear and what? It would just be a constant.
W is a matrix.
It's a matrix. So it's just telling you if I measure from here, I could couple into some other variable of the system. Yep. So it's a constant matrix. But I still assume you don't know it. You still have to learn it. Yeah. So if I do have perfect learning where F hat is equal to F and W hat inverse is equal to WU, then the dynamics reduces to this simple equation where E is just the error from where I want to be versus where it will be one step in the future and the current error. So K is just a gain matrix. So that's what this feedback linearization does for you. You put essentially the learned dynamics into your control perturbation and it tries to counteract whatever the system is naturally going to do. So you've turned it into, as far as this system is concerned, completely neutral, and it's totally under your control by designing that gain matrix to be able to stabilize the system. Okay, so just a couple slides on the next generation reservoir computer. So the whole goal is I want to learn that W and the F so that I can then turn it into a linear system. The work that I'll show you, there was one paper in Chaos that was published near the beginning of the year and one in Nature Communications that just came out a couple of weeks ago. This is more just a theoretical work on controlling the head-on map, and this is for the experimental system. So for this next generation reservoir computing that we heard about before, I'm assuming you have some kind of input data. In this case, it's Lorentz. I have X, Y, Z as the dynamical variables. I perform measurements at the current time and one step in the past, two steps in the past, so on and so forth. And then I take polynomials of those measurements, current measurements and states in the past, and then I weight them. So I'm forming a feature vector that's just a polynomial type regression of the data at current time and past times, and use that to infer one step into the future, what the system is going to do. And this is exactly what we need to do control. Essentially what you're trying to do is, here I am now, I know some past states of the system, I'm trying to forecast where will the system be one step in the future, and the control perturbation is trying to stop that, to prevent it. And just as Ed was talking about earlier today, there's got to be two phases for making a controller like this. You need a learning phase where you need to learn how the system responds to perturbation. So I can learn F hat and W hat. So the idea is that I'm going to generate some noisy waveform that allows me to explore how the system responds to perturbations everywhere in phase space. We have a chaotic circuit that I'll say a little bit more about. I then have my sensor that is measuring some projection of the states here. And then I collect that data and I know what perturbations I apply. And then I use a training algorithm, just least square regression for learning W and F. And then once I've done that learning, then I can close the loop now. I have some desired behavior, I have the measured behavior, I feed that into the next generation reservoir computer, and then use that form of the control perturbation I had a couple slides ago to then perturb the system, some knob that I have accessible.
Oh, sorry. Do you need alpha to determine the K that you mentioned? The K
No, K is something that you need to set, but you've got a limited range of values. So if you want this map to be stable, then the flow K multipliers of K have to be in the unit circle. I've got a backup slide that will show a little bit, so we swept K to look at it. You don't want to go close to the unit circle, then you're sensitive to noise, but you don't want to go too far away from the boundary. It really depends on the noise level, and empirically, in the experiment's easy to adjust that. Okay. So what we're really interested in, and this I'm putting my company hat on now, is trying to take this and put it into embedded hardware that you would find out in the field. So the idea is that I don't want to have a laptop hooked up to it. I don't want to have a supercomputer or a cloud connection hooked up to it. I want to build this controller that can go on a small microchip that gets inserted into some device. We are saying that we're evaluating this on edge computing hardware. Edge computing hardware is a current buzzword, but think of a single board computer like a Raspberry Pi. We don't like Raspberry Pis all that much because they don't have the analog to digital and digital analog converters on them that really run in real time. There's interrupts, and so you get time delays there. So we're using a very inexpensive field programmable gate array for doing these experiments. And these have 2 analog to digital and 1 digital to analog converter built onto the demonstration board. This is just one that comes from Altera. The actual field programmable gate array is maybe cost $1. It's kind of expensive on the size of things, but these essentially allow you to make a special purpose computer that can then evaluate that model. The system that we're controlling produces this double scroll type behavior. This is different projections, but it's a resistor that sources instead of sinks current, a couple of capacitors, an inductor, and then some diodes that give it nonlinearity. And so as you change how large the negative resistor is, you can see a period doubling bifurcation into chaos. So here are 3 examples of 3 different tasks that we did for trying to do nonlinear control of the system. The work that Ed was doing showed that you can control 2 unstable periodic orbits or unstable steady states. We wanted to verify we could do that too. And so there are 3 fixed points in the system, 1 in the center and then 2 in the middle of each one of the leaves. The attractor never visits the ones in the center of the leaves, so those would be ones that would be impossible to control using these older techniques, because the older techniques you have to wait for it to get close to the state, and they never approach that. So this is a case where we did the learning and now we're executing it, and we said, well, wherever you are, go to the fixed point at the center. And so it did some kind of complicated transient, and then it went there. Another one, we said, go to this fixed point, and then go to this one, and then go to this one. So I'm back and forth between the two. Started here, we turned on control, and then it was able to execute the behavior. So we're only able to feed back to one of the variables, the V1 variable, but not the V2. So we're really only controlling V1. V2 kind of follows along for the ride, but it's not some simple shape. It's because of the nonlinearity of the system. And then we also controlled it to an arbitrary state. So we essentially gave it a random waveform and said, follow this random waveform, and it does very well in all the tasks. So this is just an example of some time series data of that first task, the middle task, where we went back and forth between the 2 fixed points that are in the center of each scroll. So this is before control is turned on. The blue is the V1 variable. The red is the V2 variable, the 2 that we could measure. We then turn on control. The control signal is 0 until we turn it on. Then there's a little bit of a kick, and it very quickly follows the state. So you can't see the difference from what we requested and what it goes to. So very, very tiny error. And again, the other variable just kind of follows along through the ride, because we can't control it. Now, when we're asking it to do the transition, we're kicking the system. So this is the size of the error signal, the amount of current that we're injecting into one of those capacitors to control the behavior. So this is not tiny perturbations. That's the beauty of controlling to an unstable fixed point, is that if you're in the neighborhood of the fixed point, you can just give it a little tickle and you can keep it there. But here, we're doing full nonlinear control. You got to whack it to get it to go to the new state. But we know how to predict those perturbations that you need to apply to get it to do that. But once you're on the fixed points here or here, then the control error goes very small.
But you have an enormous control current in comparison to the voltage. I mean, this is really heavy forcing.
Yeah, you got to convert. How are you going to convert current to voltage? So this in microamps, this ends up being really, really tiny in comparison. So the control perturbations are still only a few percent. Yeah. Okay. Okay. So my time is pretty much up. So just to give you some numbers, using this really cheap embedded device, this field programmable gate array, evaluating the control perturbations on the NGRC only takes about 250 nanoseconds, which is much, much shorter than any other timescale in the system. So the NGRC is such a simple model that you can really do these computations very quickly with very little computer resources. And then my group published a paper a few years ago on trying to use a traditional reservoir computer for doing it, and using a slightly different control technique known as inverse control. In our current work, there's a lot less training data, fewer parameters, much faster evaluation, so on and so forth. No hyperbolic tangent functions, which are expensive to evaluate on an embedded device. So quite good. And then we looked at the power consumption of how much does it take to evaluate the nonlinear machine learning model. And that's usually the bugaboo. We've got data centers that are trying to learn AI stuff, and you need a nuclear power plant next to it to evaluate. So power is a big deal. It turns out that board consumes about 1.4 watts. It's mostly all the other stuff on it that we're not using. The A to D and D to A converters consume about 54 milliwatts. The NGRC is only about 5 milliwatts. And so we're running at a rate of 200 kilohertz, so that's about 25 nanojoules per inference of the machine learning model. Now, these FPGAs are not known for being low power, and especially the Intel ones that we're using. There are some other companies that make some that are 100 to 1,000 times less power hungry than the one we're using. So in summary, this next generation reservoir computer can learn the dynamics, and then you can use that to cancel out the nonlinearity to do this feedback linearization. We can control arbitrary states. I didn't show you a whole lot of the data, or going to different unstable states. And it's very easy to get this running on a tiny microchip, and it consumes very little power. Thank you for your time.